right, today we're talking about airborne applications and how do we get heat out of a system, an electronic system, when it comes to an airborne applications. Well, what are the methods of transferring heat to begin with? The first one we're gonna harp on is we're gonna talk about convection. I mean, what does it mean if I have a hot part and a cold part and I want those two to transfer heat to each other? Well, most people are fairly familiar with the concept of a heat sink. It's something where we'll use a fluid flow past some fins and we'll dump heat from one device into the heat sink and then out from there. So how does convection work?
You've seen this in your computer motherboards or something like that, where the processor has the heat sink on it, and often you'll add a fan. Sometimes you'll have components that don't have a heat sink, depending on how much heat that particular part is doing. And what's happening is that by increasing the surface area of the hot thing, I'm allowing more heat to be able to be taken off into the cold area, which in the case of those computers is the air that's flowing over those fins. And that works great as long as you have unlimited supply of air that's cold.
Well, that's nice to be able to have a supply of air. Now, if I have two parts and one's hot and one's cold, and I put them next to each other, well, we're all familiar with being able to cool something by placing a hot thing next to a cold thing and going from there. Well, there's that dividing line. Well, if we have something where we want to go from dumping heat to a fluid, but we also want to have something where we don't need a heat sink directly on it, this is a 3D representation of a VPX board and a VPX chassis. And this is an example of conductively cooling this card here. How does that work?
Well, so in an airborne application, you don't have an unlimited supply of cold air. You often have some cold air, but you might not want it inside the airplane, or you have very limited amounts of it. So in this case, what we want to do is we want to take the hot thing, in this case our components, and we want to be able to remove the heat to some place where we can then have our cold thing be available. The industry standard took this VPX, which is based on a PCI communication backplane, and developed a system wherein we can use off-the-shelf parts, or we can custom make chassis assemblies to allow us in a ruggedized compact system to conduct heat from the card into then some other system that we could use, whether that's a centralized fan blower, liquid cooling system, or whatever I might have available in my airframe to take the heat from that central cold plate and move it out into the environment.
Okay, well that's great. Now, so we have convection, we have conduction, then there's radiation. Suppose that I have a system where I don't have air available and I have these components on this circuit board here. Well, they're going to generate heat when I apply power to it. As current flows, heat's going to be generated and dissipated. But what if I don't have any fluid flow? Let's say I have a space-based application and I'm in a satellite and I'm generating heat. It's very cold in space, but that doesn't necessarily help me, does it?
No, not at all, because if you don't have any physical media to take the heat and move it off, then all that's left to you is radiation. And that just means that the part has to emit its heat as light. Now, that works great if it's a light bulb, but if you're trying to make your parts hot enough to emit heat as light, they're probably not going to perform their function very well anymore.
Yeah, dumping charged particles doesn't really help us.
Right, and so if I have a thermal mass, something that's generating heat, and I have it completely isolated, you know, imagine if I put something inside of a thermos bottle, or you've seen this if you have your laptop sitting on your blanket and the heat can't get out anymore into the air, it just gets hotter and hotter and hotter and hotter. And so once you put this in a sealed thing with no vents, no airflow, and no cold plate conducting heat out of it, its heat will just go until the part becomes damaged.
Well, that's definitely a challenge, and that's one of those interesting things with how cold it can be in space, but we just can't get the heat away from what we have. Now, what we're doing here is we're giving an overview of the different methods of getting heat away from parts in airborne applications, whether it be something that we're dealing with in a ground card application where we actually have a lot of heat at sea level or something like that, or if we're at 50,000 feet. What considerations do we have at sea level taking off versus being at 50,000 feet?
Yeah, it's a big issue. First of all, at ground level can mean a lot of things. It can mean, especially in military applications, Antarctica to Middle Eastern desert, and that means that even the air that I have that's cold could be quite warm. And especially in a sealed compartment, that air can get very warm very quickly due to solar heating. But that also can be very cold air. It could have different levels of moisture, so I can't necessarily just open that air to flow through my components because I could get condensation or other things. Particularly, this is a big issue for parts that have been on airplanes at altitude. As they come down, they were really cold because the air is really cold, but now they're coming down into warm, moist air, and then just moisture gathers just like it does on your water glass. As you go to altitude, though, you have the opposite problem. I have lots of cold air, but the particles of air are very spread out, so they can't get the heat away from the part very efficiently. So now I have to either use blowers or fans that can get a lot of volume of air to move through the piece. But again, I have to make sure that the parts are going to be able to handle that low pressure that's around them.
So it's a lot harder to come by 1 pound mass of air at 2 psi versus 14.5 psi.
Absolutely.
There's a big difference there.
Even though it's cold, it doesn't really help you very much.
Now, tying that into what we do here at Duotech is we do not just the basic considerations, not just looking at, well, thermal junctions and how could heat be dumped, but we also go to the point of doing simulations, being able to say, well, here's our design, here's the real world environment, and we take that from there, we come up with the concept, we go through and we prove it numerically, and then we move to the end result, the end product. Now, if you'd like to learn more about how we do that here, please visit us at duotechservices.com or follow us on Twitter.